Hi everybody. Welcome to this training program on transformers. I am J N Karamchetti, a graduate in electrical engineering from JNTU College of Engineering, Kakinada. I have done my MTech in electrical engineering from IIT Kharagpur. I have done a diploma in business and finance from ICFA Hyderabad. I am a certified energy auditor from BEE, Ministry of Power, and master trainer in solar rooftop grid engineer from NISC, MNRE. I have industrial experience from development engineer to chief executive officer in private limited companies and multinational companies for 37 years. I have also experience in teaching and training of engineers and executives at Engineering Staff College of India, Hyderabad for 10 years. So today we will see the operations of the transformer part 8. And this is the institute where I had my education. And the objectives of the module developed by the author is a qualified and experienced in electrical engineering, power electronics, energy conservation and auditing, design and implementation of solar photovoltaic power plants, to share his theoretical and practical knowledge with engineering professionals to improve their skills and in turn to develop India as a skill India. Now, in today's module, we will be covering accessories of a transformer. We have a conservator, holds relay, breather, magnetic oil gauge, and WTI, OTI, and radiators and bushings. These are all fittings of the transformer. They have a role to play. I'll be explaining you to the operation of that wherever is required, including some protection in this transformer also. Now let us see the typical oil flow for a ON-AN. The figure right side shows the transformer and arrows indicates the flow of the oil inside the transformer and outside in the radiators. Heat is generated in the winding. This is central portion is the winding, and heat transfers to oil, and oil gets heated up, and the hot oil flows onto the top. Hot oil flows out to cooling fins and tubes, so it comes out for the cooling fins. Oil gets cooled in the radiator. Cold oil flows into the radiator. Cold oil flows down the radiator. Cold oil flows to the bottom of the transformer. A cycle is established like this. This cycle is called thermosiphoning effect. Now, this is also the same thing. You can notice here how the oil is going inside into this. It is not going straight. It is going through this particular route, so that it is covering the winding and the gaps in between the windings where the oil has to flow. It comes out, it's a cool down and goes back through this pipe back into the transformer. So this is a normally ON-AN, but when you need the faster cooling, you can switch on the fan, so it becomes a ON-AF. That means instead of a natural flow of air, air will be forced. The forcing is because of the fan, the cooling is faster. You can notice there is a 5 to 10 degrees temperature drop in the transformer oil. These are the additional ones you can see in this OF and WF. This is a forced water cooling. That means the transformer oil comes out into a radiator, and the water circuit is also provided in this. So in this particular one side we have a transformer oil, another side we have water for cooling that. In circuits like this, the pressure of the oil should be more than the pressure of the water circuit. In case accidentally there is a leakage between the common pipes, the oil should leak out into the water, but water should not leak into the oil circuit, and be careful about it. And these are the radiators which we see here. You can see this is the flow of oil. Now when the oil is hot, here he has provided so that the hot oil always goes to the top and the cold oil comes and returns back. He has given a large surface area. You can notice that this is a large surface area, and the oil going inside is almost like a film, so the cooling is much faster. And the radiators, the top and the bottom walls are shown here. These walls you can close it to remove the radiator out for any service. So this is a one wall and this is a one wall. So you close these valves and release the bottom valve so that the oil you can drain out first and then remove the radiator for service. And you can see the transformer radiator have got two valves like this, and these valves are fitted here as discussed earlier, and this is a vent plug. As you are allowing the transformer to go, oil to go in, if there is an air, it is a very difficult, the air has to be removed. So you open this, once it gets filled up slowly from bottom to top, the last time you see when the air has gone out completely, a small few drops of oil comes, then you close that. Whereas this is a drain plug. When you want to remove the oil, you can open this, the oil comes out. And these are all the lifting legs and other things. So when you want to remove it for a servicing, you need to use some small crane to hold this and remove it. And this is the radiator. Total assembly is called the radiator. Now you can see this conservator, and you have a breather here also. And explosion vent diaphragm. This diaphragm is provided here. The whole assembly is called an explosion vent. Whenever there is some pressure developed inside the transformer because of the breakdown in the oil, because of a spark coming on that, there is a heavy pressure developed inside the transformer, and transformer should not blast. So what is done in this particular case is the air whatever is developed, the gas developed goes into this, punctures the diaphragm here, you can see here, punctures the diaphragm, and the little oil and the gas comes out. So thus the transformer is safe, but the transformer has to be disconnected immediately. Now the whole thing is called the conservator oil preservation system. Oil preservation practices are use of a COP, conservator oil preservation, for transformers above 10 MVA. 2 breathers per pipe, ensuring reliable moisture extraction and for breather maintenance, and filtration of the oil when the moisture is higher than 50 millimeters, replacement oil when the acidity is higher than 0.3 milligrams per kWh gram, and breather with heater arrangement for a continuous recondition of the silicon gel. These are also available in some of the models in India. Now you can see the prismatic oil level gauges. Now this oil level gauge, as you see it from the outside, this one, and this is the inside one, how it appears. So the transformer oil flows into this and rages into this. If the transformer oil level is up to this is called a minimum, this is called a normal, this is called the maximum level. At the time of filling the additional filling of the oil, you should be very careful that what is the temperature of the oil at which you are filling is more important. If you fill the oil at a low temperature, you can go for this. If the temperature of the oil is high, about 60 degrees, you have to see a oil should be at this particular level. Because remember one thing, when the transformer is running, the volume of the oil increases. In such case, the oil should not come out through the conservator. So this you can see the diameter is bigger. 2 glass gauges have been given, and sometimes the other side one MOG is provided. Okay. And you can see both here. This is the explosion vent, what you had seen in the other one, and conservator tank. On the conservator tank is provided, it is at a higher level. So he has gave a slightly a vent onto this. Even from a 10-meter distance, you can see the needle very carefully. The size is also bigger one. And this is a book pulse relay. Book pulse relay is always connected between the conservator and the transformer tank. You can see this is a connection, oil connection. This is a book pulse relay. When you want to remove the book pulse relay, you have to close this valve and remove it. And one more thing you should see, that this horizontal line should be maintained at least 7 degrees above the horizontal, so that the gas always goes on to the top, the oil always comes down if you provide a 7 degrees angle there. Now we have a temperature factor. We have a OTI as written on this, oil temperature indicator, and WTI is a winding temperature indicator. Crucial parameters to be monitored in the large distribution transformers and power transformers are winding and oil temperature. It gives an understanding about the overall performance of the valuable equipment. That means oil temperature indicator, winding temperature indicator will give you the performance of the transformer. Warns unacceptable thermal degradation and ensures a longer life. And these are the two photographs you can see. This is a one, this is a one. In this, there are four numbers are there. Oil temperature indicator. How it is used is when you have a fan connected there, fan will come into the operation at a as the moment the temperature crosses around 70 degrees centigrade. Okay, and runs, so the transformer oil temperature comes down. As the temperature comes down by about 5 degrees, it stops the fan running. But if the temperature still further goes, the third one will indicate, give an alarm and give you an indication that look at the transformer oil. And the fourth one will trip the transformer so that the transformer won't fail. Now the winding indicators you can see on the top of the transformer there are two pockets, they are called as a thermo well or the bulbs, inside which oil has to be poured. There is a capillary tube and heating element, thermal imaging CT and calibration box and hand dial and dry arm contacts trigger and coil. Whenever you are handling a new transformer, you have to calibrate the winding temperature indicator as well as the oil temperature indicator also. WTI, winding temperature indicator thermometer, works on the same principle as the top oil thermometer, except that the bulb is in a separate thermal well near the top of the tank. A wire type heater coil is either inserted into or wrapped around the thermometer well, which surrounds the temperature sensitive. So what is the difference between OTI and WTI? This is what we have here. A wire type heater coil is either inserted into the wrapped around the temperature thermometer well, which surrounds the temperature sensitive bulb. And the heaters warms the bulb, and the dial indicates a temperature, but it is not the true hottest spot of the temperature. Right? It will not give the hottest temperature, it gives the overall average temperature of the wind. The winding temperature is measured by the thermal imaging, a direct inference of the temperature through the oil temperature and the transformer's load current. It has an extra device, a heating resistance coupled to a thermo well and connected to the current transformer. The CT current will be generate bulb overheating and of the probe in relation to the temperature oil corresponding to the transformer loading. So this is called an image because it's not really doing the winding temperature, it is taking the oil temperature and based on the current level it is giving an additional reading. It is a calibrated one. At best they provide only a rough approximate hotspot winding of the temperature, should not be relied for the accuracy. They can be used to turn on the additional cooling or activate alarm as the top of the oil transformers do. If the tubing has been pinched or accidentally struck, it may be restricted. It can cause the dial pointer to lock in one position. The whole gauge must then be returned to the factory for a repair or replacement. It cannot be repaired in the field. On WTI, a direct measurement of winding temperature is not feasible. The device makes use of a thermal image technology. The sensing system comprises a heat-sensitive resistivity circuit through which passes a current proportional to the winding current. A potentiometer placed on the main dial allows to adjust the resistive circuit depending on the transformer parameters and can be calibrated. The liquid through a capillary will expand, producing an indication corresponding to the winding temperature. At best, the device is only an accurate at the top nameplate rated load, and then if it is not out of calibration. There is no temperature sensor embedded in winding hotspots. but it will be coming in future that a temperature sensor NTPC is being provided inside the winding itself. Advantages: accurate and stable measurement of temperature, robust design, no need for recalibration over the time, and customized mounting flange, easy accessibility to wiring, up to 4 changeover micro switches suitable to control cooling equipment and protection circuit. The gauges are subjected to insulation test between the circuits and the earth. The minimum dielectric withstand strength is 2 kV in accordance with the regulations. This is the end of the part 8, and next module will be part 9. Thank you very much to you.